picture.
Yeah, go ahead.
So, we have today, today's speaker is Dr. Uma Gorti. And so this time of the talk is not at all convenient. It's 2:30 a.m. there. But in spite of these odd timings, she has kindly accepted our request to deliver a talk. So we greatly appreciate that. So thanks, Uma. So Dr. Uma was in the first batch of the PhD students at IIA. So she obtained her PhD under the guidance of Dr. Harish Bhatt. And her thesis work was in the area of star formation. So she examined dust extinction around young stars and investigated the dynamical evolution of the clumpy interstellar medium. So after her PhD, she obtained a National Research Council postdoctoral fellowship and worked on the photoevaporation of molecular clumps with Dr. David Hollenbach at the NASA Ames Research Center, California. She has remained at NASA Ames ever since, and first as an employee of UC Berkeley and now at the SETI Institute over the past 10 years. So her current research involves studying protoplanetary disk and their evolution. So with great pleasure, on behalf of the IIA-50 Organizing Committee, I welcome Dr. Uma Gorti to present her talk on the evolution of gas and dust in protoplanetary disk. So over to Uma.
Hi, Aruna. Thanks for the introduction. I hope you guys can all hear me fine, right? So so it would be nice to be there in person, like I was just saying, but hopefully this is something we can do in the future, and maybe I hope to see all of you. So today I will talk about some work I've been doing over the past several years, probably about 10 to 15 years. And this is a sort of have a very broad kind of perspective. It's not like it's on any particular topic. So I'll be talking broadly about things that concern the evolution of gas and dust in protoplanetary disks that I've been concerned. So problems that I've been looking at for the past several years. And my collaborators in this work are listed here. These are the people that I've been collaborating with for the longest time, and some of the work that I have done with them is sort of presented in these slides. Since IIA-50, David Hollenbach, who's retired now, Kay Studemann at Heidelberg, Daniel Carrera and Anders Johansson. I worked with them on incorporating planetesimal formation, which I was going to show you, so that's kind of fun. And Maxime, who's a postdoc, who's still with me at Ames and who's done some of the work you'll see towards the later. So we all have seen this picture. We all sort of know that stars form from the collapse of molecular cloud. And this is the famous picture from the Shu Review. So we basically have these dark clouds, quartz clumps, which are supported by just thermal pressure, very cold, which collapse under gravity. And then because they're spinning, they sort of have a disk that forms around them. So the disk actually forms first, even before the central star condenses. Material accretes through the disk. This is accompanied by outflows, which is sort of what these vertical arrows indicate. As infall continues, and eventually you form the star, and then the disk is still left over after star formation. And this disk then goes on to form planets, and that's what we call a protoplanetary disk. So the first three stages, actually, we are not very sure where exactly in the stage planet formation happens, but we do know for sure that it happens in the disk. So we actually have that was a theoretical picture, it was a cartoon, but we have excellent confirmation of all of these stages now. So this is sort of a starless core. This is the dark blob that you see there. And you can see that there's a central protostar in the infrared that you can see with the Space Telescope. This is the jet and the disk. So the disk is the dark band that you see in the center, and the disk surface is sort of curved, and you're seeing scattered light emission from both sides of the disk, and then you see the jet. And in the later stages, we now have some sort of very high spatial resolution images of disks as well. So shown here as a few examples. So this is TW Hydra, a face-on disk, and you can see that. So this is a dust disk in a millimeter with gaps, and this is the disk around the calcium-15, which sort of shows more evolved and shows only the ring. And actually, it's suspected that what you're seeing out here is a forming protoplanet. So we sort of have conservation of pretty much all the stages that we thought should happen in disks. I mean, this is sort of the previous slide that you saw from Xu et al., right? And what you see in the end is, of course, a full-form planetary system. This is HR 899, so this is a disk around which you have these three planets that you can see, and these are being directly imaged planets. And so the key thing that I want you to note in the process, and something that concerns me in particular, is the fact that this disk, which first began to help facilitate the formation of the star, has through this whole process disappeared. And so the process of planet formation is sort of closely tied to the process that sort of gets rid of the disk. So the disk literally begins with star formation and ends with star formation. And and what happens to the disk is basically what the rest of the talk is going to be about. So I will first go over some observations of gas and dust and disks, sort of present the very basic things that we do observe and that we want to kind of understand and see what kind of clues they provide about disk evolution and planet formation in general. So the first thing we already know, so this is again a very old plot, but it sort of shows to capture what we knew even a very long time ago, which was that we have these four classes. And way back in the 1980s and 1990s, it was already recognized that you sort of start off with this class 0 object, which is a really cold object and visible only in the sub-millimetre, and eventually as a central star forms, you start picking up the black body emission from it. And there is still a substantial infrared excess, and this excess is basically emission from the disk. And as the object of the system evolves, the star becomes more prominent, and eventually the disk fades away. And these were roughly classified in these 3-4 sort of classes, and this is still something that's used today. And so this is sort of looking at the dispersal stage in a bit greater, in looking at different. This is again the SED, but again looking at it from the point of view of dispersal. So what's shown here in dark gray is sort of the median mass SED from Taurus, from distant Taurus, and you can see that individual objects sort of disperse in different ways. So it's not like the disk just declines in some smooth way and all disks disperse similarly. It looks like there's a slight diversity, or actually quite a large diversity, of how a disk will eventually disperse. And this is the process we're going to be concerned with, so which is why I sort of thought I'd highlight this fact that you can have dispersal occurring in various ways. So this is a disk, for example, that is where the infrared excess is uniformly decreasing. This is a disk where part of it has decreased, and you have this cold disk outside. And then you have some sort of intermediate cold disks as well. And so this again is something that you can already see that you already have structures. So these are the transition disks, and these are disks probably in the process of depleting, in that they already have these very sharp rings around them. It's often thought that these rings are due to planet formation because this is sort of dips in the dust structure and in the dust disk structure. And I must point out that there's quite a bit of controversy about, not really controversy, but there've been several explanations put forward for why you would see these rings, and it's by no means certain that it's planets, but at least this is what people in the community like to think. I mean, so most people refer to these. You must probably have seen plenty of literature which talks about planet formation in disks, and what we think is that there's a planet orbiting this disk, which is sort of carving this dynamical gap. And in some cases, like for example, the TW Hydra disk, this might very well be true. Although it's less likely for disks that are very young. So this is H et al., which is only about 500,000 years old. And it's not very clear whether planets already begin to form at that stage. But still, the point is that you basically see these disks in, this is again H et al. Disk, I think, which is seen at different wavelengths, even way out into the millimeter wavelengths. And what you can do then is you can also look at these statistical surveys, because this sort of tells you something, captures the essence of what we're trying to get at, which is how does the disk frequency, for example, decline cluster rate. So this is a plot from H, Lara and Lara way back in 2001. And what's shown here is, so each individual point represents a cluster. You can age them better, so this is a better way to do it than plotting individual stars in the map. And you can then go back and you can count the number of stars in that particular cluster with a certain excess. So this is done at various frequencies. They originally did this in the near infrared. So this is the JHK bands. And you can see already here that young clusters have high frequency of disks. And then as the clusters age, you can see that the older clusters have a lower frequency of disks, right? And so this already tells you that disks are disappearing by the time they get to be about 5 million years. So again, of the fraction, so this is again another plot. This is by reducing Spitzer and IIA bands, and you can see that sort of the same. It's with more statistics and it's in more clusters, and you can see that it's a slightly improved version of this plot, but it's still basically the same, right? So if you have sort of tried to fit any folding time scale to this, you still we have a dustless lifetime of about 3 to 5 million years. Now, the key thing about this is that it's the dust, and we think that the dust is going into planets. So this is sort of our traditional picture of planet formation. I realize I should have probably put a slide that described planet formation as well. But what we actually think happens is that the dust grains, which are sort of millimeter or sub-millimeter in size, slowly coagulate and they stick together. And eventually some process causes them to form planetesimals, which then go on to gravitationally get coalesce and form planets. So the dust, we suspect, at least based on what we see in our solar system, that it sort of mostly goes into planets. So when we say that the dust is disappearing, we really mean the solids that we can see. So these are all usually less than a centimeter in size most of the time. So bear that in mind throughout the talk, is that when I say dust, I just really mean the millimeter dust that we actually see. There could be lots of solids in the disk already, which we just don't see and still exist. And these are something that we would not really see, probably indirectly infer from debris emission or things like that. Or we might see the end stages planets when GWST goes up, for instance, and we already have some imaged planets already. But overall, the point is that, when I say dust, I just mean the small millimeter dust. And so because we know that the dust is going away, it probably means that that is sort of setting some kind of planet formation timescale. And we can do more than that. It's not just, looking at statistics to see what the disk lifetimes are. We can actually go around trying to estimate what the disk mass. This is shown here as a cartoon. So this is the star. This is a disk that is puffed up as it goes out further, and that's because of the fact that this is a vertical pressure gradient that supports the disk against gravity, and temperature doesn't fall off as rapidly as gravity does, and so basically you have a puffed up disk structure, right? This also means that the surface of the disk is sort of flared, which means it can intercept stellar radiation. And so, based on theory like this, you can construct SEDs, so which is basically this is trying to reproduce the emissions seen. This is photometry at different wavelengths seen across the entire band. And I'm looking at the slope of the millimeter because this is what the dust grains are sensitive to. The dust grains are in a size distribution, and it turns out that the mass is more sensitive to, and the number distribution is such that the mass is mostly in the larger grains. And so you can look at the larger grains and sort of assume something about the opacity, and I should sort of have all these wonderful curves by Drain here, which shows how the opacity changes when you change the maximum grain size. And you can sort of go back and you can try to, just based on the emission, which the distance to the object, you can say something about the dust temperature based on the emission, and then you can sort of use the slope to infer the dust mass. So we can do much more than just get statistics and look at how things are declining overall, but we can also sort of look at individual disks and try to see how the mass changes at the disk's age. And so this now here is a plot which shows, this is sort of a messy plot, that shows the millimeter-derived mass. Dust is a function of mass. And these are different clusters of different ages, and you can see that there is a sort of decline in age from Lupus to Taurus to Upper Skull, which is the oldest cluster in this plot here. And clearly, again, the dust mass evolves. These are very simplistic models for the dust temperatures being just fixed at something and trying to sort of get a statistical sort of sense of how the mass is going. And so that was the dust, and sort of we do know, I think I'm missing a slide, I'm sorry, but so that's sort of, we do know that the dust evolves and does things the way we expect it to evolve. So what about the gas? And we do see plenty of gas as well. So these are emission lines, and so these are this is Spitzer spectrum of TW Hydra. You can see a bunch of recombination lines and neon line, a lot of OH pumping. You also could see water. This is again Spitzer, and this is a Herschel spectral gas line emission from O1 and HD and CO in a bunch of cases. And not only that, we have, of course, maps by ALMA. So this is a CO 3-to-2 map, and you can have, you have more complex species. So you have a bunch of gas line emissions as well. But it turns out that deducing the gas mass is a lot more challenging, largely because many of these things are trace species. And it also depends on the emission line strengths, depend on excitation conditions. So it's not very straightforward to jump from the detections to the mass. So what you would like to do is do this using H2. And this, for example, is first such attempt, or one of the first such attempts trying to use H2 using Spitzer. And actually, this plot just shows the surface density as a function of H, but all of these are upper limits. So these were all non-detections. So based on the fact that this sample was within this age range, you can say, well, gas disk lifetimes are somewhere in that age range. So this is sort of a very crude way of putting it. You can try to sort of, compile statistics, which I've tried to do here. So this is the original plot is the infrared excess versus age cluster from, I think this is from Hillenbrand. And on top of that, I've tried to count, objects and tried to see, where do things lie. It looks like they sort of align. And for example, the accretion dust is known to align. So this is work by Fidele et al. Where they sort of counted, instead of counting the number of disks with an excess fraction, they counted in each cluster the number of stars that accrete. So what you see here is, again, that, it sort of follows a similar curve in that the gas disk lifetime, although very poorly constrained, seems to at least follow this sort of general picture in that it lasts for about 5 to 30 years. I should point out that there are no mass measurements, right? We'll come back to this later. So this is not sort of talking about the disk gas mass as such. So, to sort of summarize, we have the dust and disk removed in a few million years. We also know that dust disks have varied morphologies. I showed you all those gaps, and maybe they have varied evolution paths. And we've basically sort of seen that gas dispersal is not well probed, and the mass evolution is unknown, but we can still set timescales in the order of about 10 to 30 million years based on what we know. And so how is this connected to planet formation? Well, we know that gas dominates, for example, the disk mass. It's about 99% of the mass. And it influences all the physical processes just because of the dynamical cloud that it has. It sort of determines, for example, the evolution of objects. Even the clumping of the initial dust grains is affected by the presence of gas. And of course, it also affects the formation of gas giants and how frequently they occur. And this is straightforward, just because gas giants need gas to form. It also affects the formation of mini Neptunes, which are sort of the most common. So mini Neptunes and super Earths are the most common exoplanets we see. And there is some gas in there as well. So presumably there was gas that existed when these things formed. And of course, even after the planets form, if you have some sort of remnant gas left around, it would exert a torque on the orbits of the planets, and you would still have some kind of migration, for example, and affect the final architecture of the planetary systems that you see. So although we don't know much about the mass, so the gas mass, and how it evolves clearly tells you a lot about planet formation. And this is sort of one of the topics that I've been interested in. So I've been trying to figure out, and this has kind of been very interesting, and largely because it's like a puzzle. You see pieces of the picture at a time, but you hope to sort of someday eventually complete the whole puzzle. But, and I will sort of describe to you as we go along several little aspects of things that I've been working on or doing over the past several years. And the other thing we would like to know, apart from just the sheer interest in mass, is how does the gas-to-dust mass ratio in the disk evolve? And so this is sort of just telling you how the gas is evolving relative to the dust. And so this is a very interesting sort of question that I've been trying to answer, and I think a lot of people in the community have been focusing on this. And this is because this is sort of an intriguing thing about it, is that there are two timescales. So there's one timescale in which you're removing the dust, which is presumably due to planet formation. There's another timescale in which you're removing the gas, and this is mostly due to winds, and we'll talk about this later. So this is, so in some sense, these are completely different processes. So one of them is just agglomeration, and it has to do with the fact that, the gravitationally accumulating enough dust to form planets. The other one has to do with the fact that you're just sort of removing gas, and this is usually either by magnetic winds or by photoevaporated winds, which I'll get into, sort of thermally heating the surface, and you're not removing gas in dust in that process. So then what that tells you is that you could have two scenarios. You could have planet formation could be slower than gas dust dispersal. And then that will tell you that the gas to dust ratio then declines because it all starts from the interstellar medium where you have a value of about 100. And eventually what happens, and eventually you sort of have the situation where as planets form, the gas to dust ratio decreases. And that's because you're sort of just moving the gas faster than you could form planets. Another scenario is that you could have planet formation is faster, in which case the gas to dust ratio in the ISM increases from the initial value. So obviously what you have depends, will sort of dictate or influence your the kind of planets that you form. So presumably if you form some sort of initial bunch of planets initially in the beginning, and you have a lot of gas left over, then you're going to predominantly form gas giants simply because the gas has been sticking around. And on the other hand, if by the time you finish, you sort of finish sending your planets, the gas is mostly dispersed, then you're going to have a tougher time forming the gas giants, and in which case you will expect to find predominantly rocky planets. And we do know that, to some extent, we have an answer to that question, which is that, we do know that exoplanets are predominantly rocky, at least the closer ones that have been detected lately. But we would like to know more about it. And so this is one of the questions that you can look at by looking at the gas and dust and try to see how they evolve relatively, sort of answer this kind of first order scenario question, which is whether you have planet formation is faster than gas is dispersed, and then say something about the kind of planets which typically form this. And of course, we'd like to know even more, what sort of conditions dictate these processes, and when would you be more likely to form certain kinds of planets and others. But these are sort of second-order questions which we are not in a position to answer right now. So we're going to be content with just sort of trying to get at something which is as basic as this. And over the past several years, I've sort of worked on putting together a theory of disk evolution. So now I'm going to switch from sort of having given you a perspective of the kind of observations and the kind of questions you're trying to answer. I'm going to switch to sort of, a sort of a very sketchy description of theory. So, what do you expect to happen? So you sort of take all the physics you know and you put that into a disk model and try to see, well, what do you predict in terms of what should happen, right? And there are four main ingredients. There's accretion, because that's what the original primary purpose of the disk was. It was to facilitate accretion and form the central object. So that persists all through. So you have to have some prescription for how accretion happens. And then there is a photoevaporation, which is basically your dominant mechanism for getting rid of the gas. And I should add that in recent years, we've sort of also come to the recognition that there could be MHD winds which play a role. It's not very certain how much mass they remove, but there could be magnetic winds which also remove some gas from the disk. And the third sort of ingredient in your theory would be a process by which you would coagulate and fragment dust particles, because these are constantly colliding with each other. They stick and then they grow, or if they collide with very high velocities, they could fragment and sort of return the pieces back. So you need to have some way of describing this and some physics for doing that. And finally, in the end, we would like a theory for planetesimal formation, so which sort of then tells you, well, where in the disk are you likely to form planets and what rate are you likely to form them, for instance. And I should say that none of these is really well known. So this has so far been just a theory. And some of you who work on some aspects of these already know all of the sort of loopholes associated with trying to do anything. But this is sort of trying to put together our best guess efforts and try to figure out, well, what would happen if you sort of tried to put all this together and see how the disk evolves in a global way. So this is first accretion. This was something put forth by Lyndon Bell and Pringle a very long time ago, as it sort of just describes how the surface density evolution in the disk evolves. And so this is sort of the main equation. And what's going in here, this is sort of the partial differential equation, but basically conserving angular momentum and mass, and you can sort of compare. Well, what you've assumed here is a viscosity, a kinematic viscosity. This is usually parameterized in terms of some parameter alpha, and this sort of just captures our ignorance. We still don't know what alpha is, and this is sort of the holy grail of accretion disk physics all over. This is something that has confounded people for a very long time now, and I think even observationally, it's not something that's easy to determine. But so in this simple sort of one-dimensional disk, what's happening is that if you have a certain kinematic viscosity, then if you have if you start off, so this is from the original Lyndon Bell and Pringle papers, if you have a disk and if you look at the radial annulus and you sort of it's peaked at a certain time, so the surface density is a function of radius, So over time, it diffuses, and this diffusion then eventually, and it backs, and eventually that causes material to be accumulated onto the star. The star is at 0 here. But then this also simultaneously causes the disk to spread, and so you have a disk, and you set up a characteristic distribution of the disk depending on what your sound speed and your scale height also varies a function of radius. So this is sort of just telling you sort of, if you start off with a disk, you're going and if you sort of follow its evolution using something like this, its surface density is going to evolve in time, and eventually you're sort of going to have material end up at the star. So this is sort of what we're going to use for accretion theory. And so the reason this has persisted for such a long time is just the beautiful simplicity of it. You can capture everything you don't know about viscosity or how all the microphysics that's going on in the simple parameter alpha. And of course, you wanted to get fancy, you could vary this as a function of time, you could vary this in whatever it would be like. And it turns out that this has two components. There is a turbulent component and a magnetic component, and you could do that as well. But so for now, most models just assume that some value of alpha that sort of gives you how the accretion rate declines with time. And you can do fancier things, like, so for example, the disk winds, which, so this is a simulation from Ressel et al. There's a newer paper, 2020, which I sort of extends this even further in domain. And you can see that, you have sort of a region where you could have winds which extract angular momentum from the disk, and that also can give you some idea of how efficient the magnetic fields are in extracting angular momentum from the disk, because that's what you want. You want a given annulus to lose angular momentum, so it basically drains onto the star. And the sort of theory predicts that alpha has this sort of range. You can see that depending on the magnetic disk parameters, you can either have values of alpha that are reasonably high, or you can have values of alpha that are reasonably low. But we have a range of alpha that we can try out, and we have some idea of what this should be. And of course, we also have the accretion onto the star. Then it produces UV and X-rays. And at least in the star's youth, most of this is produced by accretion. They also have very active chromospheres because they have convective atmospheres. So there's some X-rays and UV to come from there as well. And we can actually measure some of this, right? We can actually detect X-rays, what the UV is. And so you know what the fields are roughly because you have all these instruments that have gone up, like FUSE, for example, IIA and Chandra, which have we have an idea of what the X-rays and UV from stars are. And so what happens is that this X-ray and UV photons then hit the surface of the disk, and what they do is they heat the gas. So this is the surface of not the dust anymore, so they can't directly heat the gas. And because they heat the gas to high temperatures and high enough temperatures, the gas can potentially escape the gravitational potential well of the star, and you could have the slow sort of subsonic wind, which is what we call photoevaporation. So you could also do this with MHD winds, of course, but again, there's still some sort of a thermal component. So from now on, I'm just going to call them winds, and I could probably mean both thermal winds and magnetic winds. So what happens here is that you can sort of solve the surface density evolution, and you can then see, and you can put in a term for evaporation. And I'm going to skip over some of this, but basically what you can do is you can find the mass loss in the disk, right? And then depending on what you're heating with, has different implications for how hot this is, how dense this is, and you can basically get an idea of what the mass loss rate is. And of course, you also then need to fold in a whole bunch of other stuff because it's not just the heating, the temperature also depends on the cooling, and the cooling, unfortunately, is by a bunch of trace species. So you have to fold in some chemistry, and you can sort of put in all these ingredients, which I'm not going to get into in great detail, but if you have questions, you can ask me later. And you also then can sort of treat cooling by collisions with dust, and of course the gas emission lines, which which we observe and eventually we'd like to connect to. So there is some chemistry in all of this as well. So the procedure is something like this. You sort of set up this disk. This is height as a function of radius, and then you sort of consider all the different heating processes, and you couple that with your chemistry and your radiative transfer, and then you sort of come up with a dust and temperature distribution, which then tells you what the photoevaporative flow is, because the hotter it is, the more the gas can, more easily gas can flow, and the density then sort of tells you something about the mass loss rate from a given annulus. So this is sort of, just summarizing the same thing, and that's kind of the theory. And then you can go, I'm jumping right into the results, right? And so this is what would happen. So you start off with a gas surface density as a function of radius. So that's your initial disk. So these are different time epochs. And you can see that the disk sort of accretes initially. And, so this is sort of a viscously accreting disk. And this is at 1 million years and 2 million years. The disk sort of slowly just expands and goes down in mass. And then eventually what happens is that at some point, you form a gap when you're removing material by photoevaporation faster than you're bringing in material from the outside by accretion. And once you do that, the disk sort of erodes pretty rapidly. And this is because what you're doing now is that you're no longer hitting the disk surface. Once you open a gap, you're sort of hitting the rim of the disk, and that means that you sort of left, you're left with just the outer disk, and which then erodes very rapidly. Then this is the disk mass as a function of time. So this is sort of just telling you how the disk mass changes. So this is not very significant, but all that it tells you is that you can, with a theory like this, get rid of disks in the few million years that you observe, right? So there is, but then again, there is a slight complication, which we sort of worried about later after we put together those first theories, which is basically that while you are, dispersing the disk, which turns out was largely due to FUV heating. The FUV heating is due to small grains, and we know the dust grains evolve because they are doing this they're forming planets simultaneously, which means that they could do, any of these things where they turbulently mix, they could settle, and then they could drift radially. And of course, you could stick and bounce and, So the point here is just that the dust disk is not static, it's evolving in time. And as the grain growth happens, it turns out that you could do one of two things. You could be decreasing the amount of UV that's penetrating and you could heat denser gas, or you could be decreasing the heating and lowering the gas velocity. And these occur in different ways in the mass loss. This is sigma dot at a given radius. And you can see that, it goes up with density. And then if temperature is going down, the sigma dot would go down. So it's not very clear a priori like what would happen if your dust disk was evolving. So we sort of tried to examine this in greater detail next. So we put together some dust size distribution, tried to use models to sort of determine what the fragmentation and coagulation equilibrium population would be at a given radius in the disk. And you couple that with the dust evolution equation, and the long story short, you basically have a dust disk. And now I've sort of moved over here to plotting this in a slightly different way. These are what are called space-time plots. So this is the radius and this is the time. And what's plotted as a heat map is the surface density. So if you want to sort of look at what's happening as a given function of time, so the radial, the surface density, you sort of at any given time is a horizontal line through here. You can see that it's higher in the inner disk and then sort of peters out as you go out, right? So this is sort of the scale of the surface density. It takes a bit of getting used to, but it's not really important right now. All I wanted to tell you was that, the disk is sort of then, you can see that by the time it reaches 3 million years, this disk is gone. And it turns out it is sort of sensitive to the level of viscosity in the disk. It turns out that if you have, high levels of viscosity, this disk goes away faster. If you have lower levels, then the disk survives longer. So this is definitely something that factors in. And this is because of two reasons. One is that alpha sort of determines the overall time scales in the disk, which is how fast the disk is sort of dispersing or sort of evolving radially. And the second factor of alpha comes in because, higher alpha means a higher accretion rate. So which means you're dumping more material onto the stars. So you get more radiation from FUV, for instance. So if you have a lower alpha, then your accretion rates are much lower. So this is something that's not well known, but but if you try to look at how the accretion rates onto disks are evolving, it turns out alpha is closer to 0.01, but measured values are usually lower. So this is still a big mess that we don't know anything much about. But looks like overall you can sort of evolve the disk even with this prescription on reasonable timescales. And now we come to, well, what's happening? So this is a confusing plot, but I just wanted to draw your attention to two things. One is, this is basically the disk mass as a function of time. And you can see that, if you, so by the time, so this sort of shows you the dust mass. This is the two lines over here, the black and blue lines. And this is the gas mass. So this is sort of the two different models. So focus just on the black line here, because the blue line is just a model without photoevaporation to show that this doesn't disperse without it, but just focus on the black line. And you can see that, as you go on, as you proceed in time, the total disk mass is the integrated disk mass. You start off with something. I started off with 0.1 in this case. And then it sort of goes down, and eventually so maybe a little less than 3 million years, you have the gas masses completely removed. But now if you look at the dust, which is the dotted line over here, you can see at the end of the phase, you haven't really removed the dust, right? So most of the dust is retained in the disk. And so this is sort of something that I wanted you to note. And this is because so far we haven't inserted any prescription for planet formation. So we really want this dust would not just sit around here, it would obviously form planets. And we've only worried about the coagulation and fragmentation, that sort of thing, and drifting in, but we haven't really worried about how planets form. So we put in a criterion for that next. So this is a movie that was given to me by Jake Simon. I'm just going to play a part of it. So let's just explain to you what the process is. So this is a process of streaming instability. What you're looking at is a phase, you're looking at the disk top down, and as time evolves, and you're looking at the ratio of, as you're looking at basically the surface density in the disk, let's say. And what you're seeing is that this clumping, so you sort of see these denser structures forming. So this is dust sort of accumulating in the disk. So the disk is basically, these dust particles are going around in a circle like this, so this is sort of what you're looking at. And what you can see is that eventually, you can see that as time goes on, you're collecting dust in these rings. And this is called something called the streaming instability. And what is happening here is that the dust is moving on Keplerian orbits, and the gas is moving slightly sub-Keplerian because it has additional thermal pressure that it sees, and so it doesn't move at Keplerian orbits. And because they have these slightly different speeds, the dust experiences a drag, right? And so, then what happens is it tries to drift in because it feels this drag, and as it drifts in, if you for whatever reason you end up collecting material, then what would happen, especially if your gas to dust went down, or the amount of gas that you have to go down, is the dust would then start trying to slow the gas down, right? So initially, the gas is exerting a drag force on the dust, but eventually the dust would sort of exert a back reaction on the gas. And when that happens, the gas is now forced to move at Keplerian velocities along with the dust, simply because of collisional coupling. And then you would end up with, sort of a traffic jam. And this is what you're seeing here. Now you can see that at this point in the evolution, we've collected a lot of material at this ring. So this is a phenomenon called, this is a theory, and it's called the streaming instability, and it's sort of the leading contender for forming planets right now. So this is, there are plenty of other mechanisms as well, turbulent concentration being one, so actually I want to pause here. So what's happening over here, what I was describing, is that at this point, Jake has decided that he's going to turn gravity on. So this is until now, we had no gravity, no self-gravity, that is. And you can see that the minute you turn self-gravity on, you form these very large clumps. And these are sort of Mars-sized objects that are floating around. So basically, this is a criterion for forming planets. And you can simplify this considerably because obviously you can't do the full evolution. So you can sort of set up criteria. So this was something we did with Daniel and Anders Johansson at Lund University. So what you can see is that you can sort of set up something based on the grain size and the gas to dust mass ratio in the disk. You have this regime where the streaming instability operates. So you can sort of use that to set a criterion for planet formation. And now again, this is a plot which shows the surface density evolution of a disk without the streaming instability. You can see that this is the same as the previous model, where in about 3 million years, you completely got rid of the gas. This is the surface density everywhere is negligible, but the dust was left behind. And now clearly, if you have the streaming instability, what's happened is that you have lost the gas disk, but you've also lost the dust disk. And in this case, the dust is being lost to planets, right? And you can see there's a little bit of debris dust that's still left over. So there's a little bit of dust that still stays down in the system. But what's happening over here is that as you're removing the gas, you are triggering the streaming instability, which is then converting a certain amount of the dust into planetesimals. So this sort of gives you some rate at which planetesimals form. And then we tried to, in this paper, sort of see how much mass you convert into planetesimals, and it turns out, so this is mass as a function of time, how much you accumulate, so these are the different size bins, and this is your planetesimal mass, and you can see that, you can form planetesimals reasonably quickly. It's not actually that quickly, we sort of took time, and we converted about 70 Earth masses of dust into planetesimals. This is something I'm going to skip over. So to sort of recap of what we did, so I'm going to go back into other things now, but just to sort of summarize is that we learned that disks, in these models, disks lose their mass by accretion onto the central star. You lose both gas and dust. We know that winds remove gas from the surface of the disks, but they're not dense enough to carry along dust because it's decoupled to the flow. And therefore, the dust mass will increase relative to the gas. It promotes instabilities, and because planetesimals form, and then it's possible that the dust decreases again. So this is sort of what happens. And what we find is that the disk is ultimately dispersed by photoevaporation on a few million year timescales. And because of the fact that the planet formation process is tied to the gas removal process, especially for the streaming instability, this is true. And actually for most methods that have been proposed, or most sort of processes, most mechanisms that have been proposed for planet formation rely on this lowering of the gas to dust ratio. It turns out that if you can somehow get rid of some gas, or even a third of it, you can promote a lot of these planetesimal formation processes. So it looks like it's, at least from the face of it, like it could be a self-regulated process where, you're removing gas and dust on similar lifetimes. So of course, what you want now is that this is something that I've been looking at recently. It is, or rather in parallel, is trying to actually measure gas disk masses. We've already established that, we can see tons of lines, we have a lot of information, but we only have information from trace species, right? So this is one of our main problems. We're not looking at H2, which is the main molecular constituent. And so we're sort of trying to see, well, can we test these theories of disk evolution? And this now comes back to more modeling. And these are just ingredients. So you're sort of now trying to do things, so this is sort of the same thing as we mentioned with photoevaporation models, but I've sort of just point out here that, you need to worry about all the heating ways you can heat the gas, the ways you can cool the gas, and then you have to worry about some rate of transfer. You have to attach that with some chemistry. And then you can sort of, prescribe some surface density distribution, use your vertical hydrostatic equilibrium solution, some equation of state, couple all of this together. And the idea is that you can then come up with density, temperature, and abundance information in the disk. So at every point, you know what these three things are. And once you know those three, you can sort of then go back, compute your excitation, and then compute your line emission. And you can do that. So we first tried to do this for TW Hydra. And what we did was we used a bunch of surface line emission features. So we used H2 and OH and Spitzer and Neon 2, forbidden line emission from O1. So we started trying to look at things across, multiple wavelengths and trying to reproduce using the same surface density distribution, all of these in a self-consistent way. Now, remember that, all we're doing here in the previous setup is we're sort of specifying the surface density distribution. The rest of it is all being computed, right? So what we can do is just keep varying the surface density distribution and sort of go through this whole exercise, because all of this sort of depends on each other, and try to see, well, what sort of predicted line emission do you have, and how does that compare with what's seen? So we sort of did this, and we came up with a massive disk for this star, for this particular star. It was also almost a tenth of the stellar mass. But then it turned out that somebody else who did sort of try to do something very similar came up with a mass that was almost 2 orders of magnitude more. So clearly, your mass is not something that you can just measure. It depends very sensitively on the model. So you need something to trace it. So a straightforward way to trace that, because obviously you can't see H2, but with Herschel, you could detect the HD 1 to 0 line, which is the main isotope. And it has the simplicity in that, that its chemistry is not very complicated. It just depends on the abundance of deuterium, which we can assume. And it turns out when you did that, the mass was pretty high. It was aimed at, it was sort of closer to the value that we had derived. Now, the problem here is that Herschel's gone and measured HD for only about, this was the only disk which had a clear, strong detection. There were 2 more which had only a 3 sigma detection, so we don't have any way of measuring HD anymore. So then we turn to the next isotope that we can see, which is CO, right? So this is sort of the next thing, because the next most abundant thing that we can think about is CO. CO turns out to be extremely complicated, and that's largely because it freezes out. What I have here is just the results. So this is from a Lupus survey of Lupus Alma survey. And what you're looking at is the disk mass for different objects. So what's on the x-axis here is just the identification of various sources in the Lupus survey. So what they tried to do here was measure the dust mass and then measure the gas mass using the CO isotope emission. And then they find that if you try to plot the gas to dust ratio, which remember this is what we're interested in, it turns out that they find that the gas to dust ratio has, in some cases, in lupus gone down substantially, right? So this is interesting for planet formation, because then they're sort of telling you that you're directly probing planet formation. But then, because of the fact that the C18O emission is not straightforward, there could be some chemistry going on. So people have two favorite interpretations depending on whom you ask. There are people who favor depleted gas disk, and there are people who favor some change in the carbon ratio due to the chemistry in the disk. And this is also sort of interesting for planet formation for reasons I won't get into, but it sort of has implications for exoplanet atmospheres, for example. And again, you can sort of, so this is sort of just a rehash of the same thing. So this is a Williams and Best paper, which tried to model the CO line emission and put various observations on it. And this is another paper by Kauma, which tried to which prefers the interpretation that the chemistry is different, and tried to derive the C to H ratio. And for TW hydro, for instance, they found that the C to H has gone down by a factor of 100. And this is another paper which is trying to do the same thing. So there are sort of two different lines of thought. So one is that the chemistry is funky and something is going on as planets form. And the other is that the gas is just getting straightforward depleted, which is why you're not seeing CO. And so I jumped into this whole mess a few years ago. So this is sort of my latest, thing that I've been doing, which is sort of trying to get this, the gray surface chemistry and disks to understand what's going on. And there's sort of two reasons for doing this. One is that we have all this, fabulous ALMA information. So you can see this is a survey of this particular object, and you can see this is the emission as a function of radius, and you can see that there are all these structures in the disk. So this is the dust continuum, is the purple, and you can see that things like TCN, HCO plus, and N2H plus, they seem to have this ring-like structure. It sort of peaks at some radius, and there are sort of all these cool maps that you get, and it's sort of interesting to see what the chemistry is like. And most of this is happening in the cold disk, which means that and there's observations of complex organics like methanol and metal cyanide, for instance, which seem to suggest that in these outer disks, all this chemistry is happening on the surface of grain. So this is kind of very similar to how H2 forms, if you remember from your days of coursework, that so H2 forms but when two H atoms collide on a grain, and then sort of, they find each other, form H2, and that's sort of the dominant mechanism by which you form H2 in the galaxy. And this is sort of very similar to that, in that the grains sort of form this sort of surface where, and as a catalytic surface where things sort of, collide on the grains and then find each other and then form molecules and get dissolved. Or sometimes they just form molecules and stay on the grain itself, and, are bound to it and get dissolved later when you have, something to dissolve it as the grain warms up, or you have UV photons or something. So this is something I've been looking at, and partly because it has implications for what's going on in the midplane, which is where all the action's happening, which you can't really see. But grain surface chemistry sort of allows you to look at some of that. And we sort of, so with this postdoc, Maxine, we've been trying to, put in a whole bunch of the physics in here. Now your chemistry has sort of substantially expanded because you're considering things on the surface of the grain. I'm not going to get into this in detail. This was a slide made for a different purpose. But the point that I'm trying to make is that here, so what we find is that on the surface of the grain, you actually can end up forming CO, which freezes along with water. And because of that people have been so far, so what happens here is that, you have this is the height. I think this is probably an overly complicated plot, so maybe not look at it. So the main bottom line here is that you have photoprocesses that dominate the gas phase abundances of everything you see. And by that I mean is, UV hitting the surface of the disk. So when the grains get cold enough, like, so let's say around 100 Kelvin, is where water ice on the surface of the grain freezes. So basically water ice just drops out of the gas phase. It sort of goes entirely onto ices. And it turns out that what we find is that when that happens, pretty much everything freezes with it. So CO and all the other species freeze with it. So the midplane is basically this layer where you have ices and nothing else, right? And We also find that doing this consistently is important. And once we do all that, what we find is that we can then go back and look at the emission. So this is a map of the emission of HD and CO, which is basically two of the things that I've seen. We can sort of calculate what their abundances are and what their and what the emission is from there. And what you'll see here is that in the case of HD, if you look at the disk midplane, it's not frozen. But on the other hand, it has a high excitation state. So it's got about 130 Kelvin that you need to excite it. And so the emission is again dominated the surface. And the same thing happens for CO, right? So CO is not even present in the midplane because it's excited at very low temperatures, right? But then it freezes out very rapidly. And because it's frozen out, you're again sort of missing this key midplane layer, which is what you're interested in. Remember that all the grains and all the planets are sort of in the midplane here, which is where you really want to know what's going on, but all you're looking at is the surface. So even with our best tracers, remember, we don't even have any facility right now that we even look at HD, but if we did, assuming that Herschel was still up there and running, you still are looking just at the surface, right? So this is sort of the key thing to keep in mind. And so actually I missed a plot, I'm sorry. But what I wanted to show you was that the line luminosity that we compute is consistent with what's observed for lupus. And I think when I was trying to put this together, I think I deleted the wrong slide. But there was basically a bunch of lupus points on this, which sort of showed that you didn't need to deplete CO, you don't need to have any funky chemistry going on. You don't really need anything, and you don't need to deplete the gas either. So it turns out just accounting for this freezing process takes care of the observation that we saw a while ago, which was the C18O lines surveying lupus. So what we conclude is that, we still find that the gas to dust ratio stays to be 100. So we're looking at really evolved disks. We started out with an ISM value. So this is the same slide I had before, but remember we were trying to look at how the gas to dust ratio evolves as an indicator of what happens with planet formation. So it turns out that, you started out with 100, and as you keep, the disk evolves, you sort of stay at 100. And the suggestion there is that there's some kind of self-regulation, right? Because as we've talked before, this is what we expected sort of in theory, is that if you have planet formation, then you first need lower gas to dust ratios. You need some gas to be removed, and this happens due to some winds. But then as planet formation proceeds faster, then what happens is that the gas to dust will go up because you'll be removing dust faster, and then the planet formation stops. So it's some kind of a self-regulatory process is what this suggests. Of course, we need a lot more observations to do that. And this is kind of another tack we've been following over the years. This is now trying to look directly for evidence of winds. And you can see that this is a mess, but what we've been trying to do is look at resolved observations of forbidden lines. So these are optical lines, and the CO and the 4.7 micron lines, this neon lines. And what you see here effectively is a purple. For example, if you look at this particular object, you can see that there's a slight blue shift, and the fact that it's single peaked and very rarely, shows the double peaked Keplerian signature indicates that this is in a wind. So we're looking for wind tracers, and this is actually quite something that's been quite challenging to do. That what we think so far, based on sort of trying to synthesize everything we know about what we've learned so far in one plot, which is that at early stages you have winds, and then as the disk evolves and you form planets, in the MHD winds, sort of the magnetic winds peter out, the ones that sort of drive accretion, and then the outer disk is removed by photoevaporation. So this is what we think happens in the disk, but this is very much work in progress that has not received any, that still needs to be looked at more carefully. And of course, I also wanted to point out there's plenty of stuff I've ignored, like I haven't treated the disk winds in any great detail. But of course, this is the whole viscosity in disk and the accretion, how accretion proceeds, which is an open question. And if you have planets, so for example, this is a planet that's carving a gap, and if we did have a planet, it would, determine how gas went past it, and so that would also affect disk structure. And there are a whole bunch of things that I haven't talked about, which are like, you have dust traps, pressure pumps, which collect dust, and then of course snow lines, which could affect how the chemistry proceeds, and so on. So this is. So the bottom line is that everything I have said is to be taken with a grain of salt, because there are many processes that have not been accounted for. So this is my summary slide. And you can see that, so basically what we have concluded is that disks accrete almost half the gas mass and dust in early stages of evolution, and the rest of it is removed by photoevaporation. We find that dust and gas evolve differently. Most dust drifts in and makes planetesimals, and gas is lost by winds, but the mass loss rate's not measured. And when you try to sort of look at both of them together and try to look at it in various different ways, looking at emission lines and looking at statistics and sort of trying to construct a theory, it looks like they evolve, even though they evolve in different processes, they evolve to keep this ratio nearly a constant. And the caveat being that we still don't know very little about planet formation and chemical evolution as the planets form. So that's sort of a summary of what I said so far. So thank you very much for staying on. And I hope it wasn't an overload of information.
Thank you, Uma. It was an excellent talk. And I would like now to open the floor for discussions. So if you have any questions, participants, then you can unmute yourself and you can ask the question.
Can I ask one, which is, I don't know if it's completely related to this or slightly different one. Maybe since he's an expert in all of these things, I just thought of asking a simple question, which is bothering me, is the planets formation in a cloud which forms single stars versus a cloud which forms, say, clusters. It has any bearing on that?
A little bit.
Do we have any statistics, even observation statistics? On?
Yeah, we do. I sort of, yeah. So the problem here is that, so the nearest star cluster forming region is Orion, right? That's like at 450 parsec. So hopefully we'll shed more light on this with JWST. So this is kind of, it's kind of like that story where where person's lost his keys and looks near where the light is. So basically, what we have is we have information from the nearby star forming regions like Taurus, and these are all mostly isolated, right? Okay. And that's the information we are trying to match right now, and that's because that's just what we know, right? So we don't have as much information about clusters. We do know that, and there's maybe plenty of work by Kathy Clark, for example, and collaborators where they've looked at disk lifetimes in clusters. And yes, if you sort of go, if you are in a suitably high radiation field, so you have to get reasonably close. So let's say you have an O star cluster, right? And you have a central O star and you have this cluster with a bunch of low mass stars around it. So the ones that are right near the O star definitely have disks that are eroded by it. So this is what's called external photoevaporation, right? And then that would mean that you sort of got rid of the material, and it's quite likely that you've gotten rid of a lot of it before you form stars. But you would still retain, for example, the inner 30 AU or 20 AU unless you got really close to the star, right? And this is where we think planets form. So it's quite possible that this is happening independently of the outer disk, but maybe they form planets with less efficiency just because you've removed a lot of the mass. But we don't know that much about it, right? And most of the stars in this cluster are not going to get that close to the O star So yeah, and so we think that in that case, it'll probably proceed very similar to the low mass star forming regions. But this is something that still remains to be studied because we don't have information at the level of detail we have in the nearby star forming regions like Taurus and Focus, for example.
Okay, thank you, Uma.
Sure.
Nice.
Uma, this is Sujan here.
Yes.
I think your speed remained the same after 25 years.
Really? I thought I slowed down.
No.
That's not good to hear.
I thought of saying something. How are you frozen in time?
Really?
I'm curious to know that what happened to the magnetic field of the disk. Does it contribute to the planetary magnetic field at later stage? Or it is very
yeah, so I think very little is known, right? So all we know is I think they have some meteoritic evidence for some one Gauss field in some meteorite or something. You can't measure magnetic fields. People tried to look at polarization with ALMA, for example, right, and tried to sort of thought we could get magnetic fields, but then it turns out that all the polarization you see in ALMA is basically due to the dust cell scattering, things like that. So you really have no idea of what the field strength is, right? So and actually it's far removed from what you're asking. You're asking a question that is much more later stage. This is like the evolution of the magnetic field. We don't even know what to start with, because, you know, I think people that have, people that do studies of core collapse, for example, right? They don't even know where the remnant magnetic, where the magnetic field is coming from. Is it remnant or is it generated in the disk, for example? I think those are all very open questions. It's very little is known about it.
Thank you.
Uma, there is a question in the chat box. Would you like to take it? In the chat box.
In the chat box, let me see. Who access the chat box?
You can ask Swastik, you can ask the question.
I can
Read it.
yeah.
Okay, well, read it. Yeah, I think I can't find it.
Yeah, Swastik will find out. He is the one who's asking the questions.
Yeah, hello. So that was a nice talk. So my question is in your slide 22 and 21. So that Q, is it Tumre parameter? I just wanted to know.
Yeah, it is.
So can observationally you can make any condition whether the instability will happen based on Tumre parameter?
So, I mean, there are disks, like Alma has seen disks with spiral arms, which we think is like, you know, the m=1 spiral. And I recommend you look at this. These papers called, there's a whole series of, it's a large program called D-Sharp by Alma, which was 2018. So it's by Andrews et al. And there's a whole series of D-Sharp related papers. So there they do have 3 disks, which they think should look like they have spiral arms and could be unstable. It's possible. I mean, at the early stage, at least we do expect this will be unstable, right? Because we think they're going to be quite massive. But this is all way past that. So most of my talk is focused on later stages where we're looking at.
If I come there by, say, 5:45, is too late for you?
Yeah. Hello, can you hear me? So there's one more question I have. In your slide 30, it seems like there is an upper limit on the radius. Can you just go there? So
this
as
one?
we can see, yeah. So is there any upper limit? Like you can see that for gas surface density at 10 to the power 3, it's just the radius is around 10 cube, whereas if you increase it, it just comes before. Can you just say why is it so?
Yeah, so the reason here is that, okay, so if let's say we had a purely viscously evolving disk, right? So this is an artificial initial distribution. So if you look at this one, so the next one, for example, at t=1. So this is kind of a, you know, a viscously evolving disk. So what would happen if we didn't do anything and just let the disk viscously evolve? Is that it would cause spreading. So remember, if you remember the Lynden-Bell-Pringle sort of thing where, you know, you're accreting, I mean, I had that slide somewhere, right? So if you remember the ring that, I think it was before this, right? So if you remember this ring, right, this is just a way of looking at it. So this ring sort of just spreads out in time, right? So the stuff accreting, but material is also simultaneously leaving out. And this material is what's carrying away the angular momentum. So if you just had pure viscous accretion, this would sort of just evolve all the way. It just keep going out, right? So you would sort of end up with a disk that's infinitely large at a given point. But what's happening here is that you are removing material more efficiently by photoevaporation in the outer disk. I didn't get into the details of this, and this is just because of the fact that, you know, your temperature is a very shallow function of radius. It's like goes as r to the -1/2 or something. But gravity is falling off much faster, right? So as you go out, it becomes easier and easier to remove material.
Should I get...
Yeah, so basically what happens is that as you go out, it becomes easier to remove material. And that's what's sort of keeping the disk at a smaller radius. You see what's happening?
Yeah.
Okay.
So in this plot you have shown, just follow-up question. So in this plot, the maximum radius that we can have is around 10 cube. So so you have an upper cutoff limit, right, for every star, that what could be the maximum radius?
But then we don't, you have to remember, I thought I sort of said, I specified in the beginning, right, is that you don't know what the viscosity in the disk is and how fast this evolves. So let's say if I had, this assumes alpha is 0.01, right? If I had alpha of 0.1, for example, right, it would be very different from an alpha of 10 to the -3. Yeah, so it depends on that, something which is unknown. So it would change from distance. So this is a theory, right? I mean, so it's like, and in reality, this assumes one set of parameters. For example, this is a solar mass star. It has a certain UV flux, and a certain temperature, a certain everything. But if you, I don't know, but there is a whole range of everything. So you can sort of vary this and you probably get a whole diverse set of outcomes.
Oh, okay.
Hi, I don't know. This is Manoj from TIFR. Can I ask a question, please?
Oh, sure. Yes. Manoj,
Yeah.
please go ahead.
Yeah, Uma, this is Manoj.
Hi, Manoj.
Yeah, hey, great work, excellent talk. I just wanted a question about the gas dispersal timescale that comes out of your models. That seems to be very fast. Correct me if I'm wrong. So in 2 to 3 million years, the surface density of the disk is decreasing by significantly dropping, and then by this mass is going down from 0.1 M-sun to 1,000th of M-sun. So I was just wondering, because a few million-year-old disks have accretion rates of the order of 10 to the -8 solar mass per year. So your photoevaporation rates have to be significantly higher than that for this such fast gas dispersal, no? I mean, how does it work?
Yeah. So that's basically something that I have not looked at. I mean, I have not shown here. But the accretion rates are, so if you take, I think this model, maybe it's this one. But if you take a typical disk, right, so now there's a whole range of numbers you can get, right? But if you take a typical disk and you take a typical FUV field and you take a typical X-ray and you assume, you have to assume alpha is 0.01, otherwise this doesn't work for whatever reason, then you do get the accretion rate to sort of go according to what's observed. But then again, I'm not very confident in saying that because it is sensitive to alpha after all. So I could, you could tweak this. So for example, and I had a plot, I think later on, that showed how sensitive it was to alpha. So I can go from 3 million years, for example, to 13 million years just by tweaking alpha by a factor of 3, right? So there are, I mean, I think at this point, you have to look at it more qualitatively. And so it's possible to get a whole range of outcomes. But I think that I sort of still favor the 0.01 because this sort of best explains things you have. And I didn't sort of elaborate, but in the plots, we do sort of assume there's an inner MHD wind which sort of obstructs the FUV. And so there is no photoevaporation in the beginning, which is probably why you see that initially the disk is evolving just viscously.
Yeah, but then one corollary to this is that your photoevaporative or MHD flow mass loss rate has to be higher than 10 to the -8, significantly higher than that to disperse gas this fast, no?
No, not really, right? So let's say if I did nothing, and so I started off with a very high, let's say I start off with an unstable disk, and the accretion rate is 10 to the -7, and I've done this too. I haven't published it, but you can start with a really massive disk and have stuff accrete, just by gravity, like you sort of set up.
Such disk will not be stable gravitationally. 10 to the -7 for it, around a theta stars will not be stable.
Yes, exactly. No, but you can sort of, you can accrete the disk, right? And then you can wait until the disk settles into the cubicle one stage, where things are more stable, right? And then initially what happens is that you just kind of, the accretion rate just declines with time, just viscously. And that's kind of what you're seeing. So if you go back to the Fidel plots, which I showed, which had the accretion rate as a function of time, like the sort of, right at the beginning, there, what will happen is that, I think it was even before this, right? Let me just go back. Oh, wait, I thought I had the Fidel plot. Wait, hold on. Why does this not work? I don't understand why I can do that. So you see, it had these plots by Fidel here, right? These are the accretion rate going down as a function of time. So this is just accretion. It's just accretion. So if I just assume an alpha disk model and I plot it, I will get this. And then at some point, the accretion rate has dropped low enough. So most of the time, the accretion rates that we get are something of the order of a few times 10 to the -9. So
but that happens after 5 million years. So your gas disks seem to disperse in 2 million years or so. That's why I asked this question.
No, but okay, so I thought I explained that. That depends on alpha, right? So when I get to that point, so when I get to, so in this case, this particular model, like let's say I've gotten here in 3 million years, right? So it depends on when my alpha drops to, let's say I can just fix this at 10 to the -9 is the solar mass, is the mass loss rate that I have. So I have to wait until my accretion rate drops down to 10 to the -9, right? That's when photoevaporation takes over. But when it drops 10 to the -9 depends sensitively on what I assume my alpha to be. So that's why the lower alpha takes a longer time, because I have to just wait. Nothing happens. You're right in that initially nothing is happening. So it's only at the later stage that when the accretion rate dries down that the disk actually starts dispersing.
Okay, thanks.
Yeah, you could shoot me an email. I mean, I have a feeling I didn't answer your question, but
No, yeah, that's okay. We can talk about it later. Yeah.
Yeah, sure. Yeah.
So are there any more questions?
Yeah, this is Annapurni here. So I was just wondering whether, I mean, your last slide, you mentioned again that the gas which is escaping from the disk is not detected.
Yeah, right towards the end.
Yeah, the very last slide which you stopped with.
These?
The last slide you stopped with the summary?
Yeah.
So the third point, the gas disk mass is lost by winds. By photoevaporation, mass loss rates not measured. So is it possible to measure this?
We've been trying for the last, I think, almost 8 or 9 years now.
Okay.
So, there's all this NSF funding, I think it's been devoted to just that one particular point. So we've had this collaborative project. We're looking at all sorts of things.
The day you could the day you measure, your NSF funding stops.
No, but hopefully we measure more. No, we've been trying for a while. I mean, it's just that, we don't have, so when we have sensitivity, like, even with JWST, I mean, the deadline was yesterday, right? So we've been trying to do the same thing now because we're trying to sort of, again, get mass loss rates from JWST. So JWST, unfortunately, now has sensitivity, but it doesn't have resolution. So you can't tell where things are coming from. Like, I think you need too many bits of information, and we don't have it. We need the densities, we need the extent of the wind, so we need spatial resolution. Then we need to figure out the temperature to sort of map the emission to excitation. Then we also need high velocity resolution because these are just like, a few kilometers per second. So I think the best we have from the ground right now is about 7 or something like that. I think we have some data at 2 kilometers per second, but even that is not enough. So yeah, it's just challenging, I think.
But if you go one at a time, I mean, of course, there are a lot of parameters, but what is the easier to tackle?
Yeah. So we do have, so that is kind of something I didn't mention. So, there are papers here that I've cited if you're interested, but these are all papers that I've worked on. So this paper, this is our latest work that came out just a few months ago. This is actually another one that I haven't mentioned here. But so when you see the emission line like this, right, this is all you're really seeing. So let's say I pick this particular plot. I'm going to go to the one. So let's say I pick this plot. You're just seeing this purple emission line. So this is O1 and this is, neon 2 that you see. You don't know where it's coming from.
Yeah.
Right. So you don't know the extent of the wind, right? You just know the velocity. So you can sort of, it depends on how extended this is. And we don't know that. So there's always some uncertainty on the other with different data. So like now with JWST, we'll probably get the extent, but we don't know the width. That's I mean, hopefully you can put it all together, but that never seems to happen. Somehow you can observe some disks from some places and you can observe a completely different set of disks from other places. And I haven't even managed to, I've been asking my observer colleagues for a while. I haven't tried, we've got very few disks where we have all lines available, for instance. We have some disks where we have this, some disks where we have that. And even just putting together the different tracers will tell you something about the density, right? But even that seems to be a challenge. Yeah. So this is it's not easy. That's all I can say. Yeah, everybody would like this. I think if you knew that, then, even for MHD events, which, you have, very little about things, how accretion proceeds, for example, right? I think even jet mass loss rates are not that well determined. If I know that there's some controversy there also. So, yeah.
Thanks.
Uma, did you say something about proposals to JWST? JWST had to be launched, It's another year.
The deadline, yes, but the deadline was yesterday. So this is the first cycle.
Even before, okay.
Yeah, so the idea is that as soon as it's launched, then you start observing, right? So have everything ready.
3 months before, 6 months before.
Yeah.
Okay.
Yeah, so by the time I think the TAC meets, it's probably going to be February, right?
Okay.
Yeah, and then I think by the time launch happens, I mean, launch is still slated for March. Let's see. It keeps slipping. Somebody was saying the JWST launch is always 1 year from now, whenever you are.
Yeah, like a 10 years from now.
Exactly. Yeah, no.
Reminds me of AstroSat, but finally it went. Yeah.
Good. Very nice talk. Sure.
I have a question. Is it okay if I ask? So Professor Gorti, the constant dust to gas ratio of in the protoplanetary disk, is it so? Will it will have some bearing on the kind of planets that are forming, right? Will you be able to comment on something on that? Like if there's a constant gas to dust ratio throughout the lifetime of the disk, won't it have strong implications about the kind of planets that we are detecting?
Yeah, it will. So that's kind of what, so initially I was expecting to find one or the other, right? So if you have a gas to dust that's very low, then you expect that, okay, you form one kind of planets, right? I mean, this is not the slide that I should have been on. I'm having trouble with my slides, I'm sorry. Yeah. So if you had, if you had a value that was much lower, then you would think, well, you're forming mostly rocky planets. And if you have a value that's very high, then you're forming probably gaseous planets. I think that where we are right now, which is, sort of in this value, it's not really 100, but, it's close to 50, 60, but we have sufficient gas in there that you're probably forming gas giants, I think. And then maybe like in our solar system, right? So we think that Jupiter formed and then influenced at least theories of our solar system formation, claim that, based on all the meteoritic evidence, and I think it's sort of an evolving picture even now, is that Jupiter formed and sort of shielded the inner disk from volatiles, which is why our solar system is dry inside of Jupiter, right? And then outside Jupiter, we have sort of more volatiles, like we have the gas giants, and then we have the Kuiper belt, but that's full of volatiles as well. So it could just be a process that happens later, but I think at least based on the limited information we have now, and I was again also reiterate that we only checked with one star forming cluster, right? So we only checked with lupus because there isn't data. So if there's more data, maybe the picture changes. I don't know. And this is just we just checked with lupus, but right now it looks like there's sufficient gas and there's enough to form gas giants. So that's all I can say.
So the intermediate value about 50 or 60 that you are saying that we usually detect for gas to dust ratio, would it also be possible? Is that an explanation for the overabundance of super Earths and mini Neptunes, because these are neither rocky planets nor they're gas giants? So
but it's a complicated process. See, so we don't know enough about planet formation, so I wouldn't hazard a guess, right? I mean, I'm guessing at this point, so my guess is as good as yours, right? So it's just that at some point, there are other things that are happening. So let's say now, like I said, in my second to last slide, that I have not considered structure from, so for example, if you look at this simulation by Xiaohan Chu, there's a disk and there's a planet in there, right? And you can see that the streamers, the outer disk doesn't just make it to the inner disk, it accretes onto the planet, and then there are these horseshoe orbits, and then material trickles past to the inner disk. So once you form a planet, then things could change again. So we don't really know that. But definitely looks like there's at least some gas around, which does explain the super Neptunes and super Earths and mini Neptunes that you see. So because they are sort of have some ice around them. But clearly there wasn't enough gas to make them gas giants. That's the thing.
Thank you.
Yeah, sure.
So, okay, so if there are no more questions, then let us thank the speaker again for a very excellent talk. Thanks, Uma. Yeah. And thank you all the speakers, all the participants. Yes. I'll now formally close the meeting.